All right, folks, we're going to go through this example problem here. With locked brakes, meaning the wheels aren't turning anymore, a 2,000 kilogram car slows from 30 to 25 meters per second in 2.6 seconds. And I'm going to just, what can we figure out from this? What can we solve? So, how do we even get started with something like this? The first thing to do, always sketch the scenario. So here's maybe the road. And we've got ourselves a car. And here's the car. We'll draw it moving to the right. This is what cars look like. Oof, that was a particularly bad car, but it doesn't matter. That was better, at least. I tried to draw the doors over here. It was no bueno. That's okay. There we go. The car has an initial speed of, let's see, 30 meters per second. And it's going slower in the end at 25 meters per second. And we want to, let's see, choose a system next. The system, I think, is the car. I think that makes the most sense. So that's our system. We'll draw a dashed circle around it. And I'm going to keep annotating this with some other things. First, what direction is the velocity change? I'm moving to the right in this picture, but getting slower. And so my velocity change is to the left. I'm going to keep that in mind because the velocity change is where the physics is happening. What else? I need to throw a reference frame on here. So I'm going to draw myself a number line. The positive x direction is here. I'm going to choose my car starting at 0. I think that makes sense. That's a choice I get to make, but I'll say it starts at 0 meters. And this is, oh, we don't know the final position, but I bet we could figure it out. So let's just call this x final for now. This will be something we figure out. I think we are all set to go now. Maybe we want to draw some more things. Free body diagram problem. I'm going to take this system, shrink it down to a single point particle. And let's see, what forces are acting on it? There's the downward force that the Earth exerts on the car. There's the upward force that the road exerts on the car. And then there's, let's see, something slowing it down. It's moving to the right, but it's getting slower, so the velocity changes to the left. That means we need a force slowing us down. What may that force be? Well, it's going to be friction, but we'll call it another force that the road exerts on the car. We'll learn in Chapter 4 that really these are two sides of the same force. The piece of the force perpendicular to the road, we'll call a normal force later, and then the piece of the surface force that's parallel to the road we'll call the friction later. But this will work for us for now. And I'm going to say that these two are equal, and we are ultimately, we can figure out how strong that force is. All right. So we can figure out how far it goes. We can probably figure out, well, we know that, let's see, we know the time actually. So let's actually go through. One thing I should have done early on is actually annotate the problem. So let me go back and do that now. With locked brakes, the 2,000 kilogram car, we know its mass, slows from 30 meters per second to 25 meters per second. So we know its velocity initial and final. Then we know the time interval over which that happens is 2.6 seconds. So I've underlined the physical quantities that are given to me. And then I've sketched each of those into this except for the time. And usually I just do that by drawing a clock and drawing delta t equals 2.6 seconds next to that clock. All right, so now I have set up the problem. This is step one for sure. Taking the words, translating it into a sketch, throwing a reference frame on that sketch, including where my choice of 0 is and which direction is positive, and then drawing a free body diagram of the scenario. Remember that we don't need a force to the right, even though we're moving to the right, and the reason is because we're getting slower. This force isn't causing us to move to the right, it's causing us to get slower, which is a force opposite the direction we're moving. All right, with this setup, I am set to, well, so what don't I know? I can also answer that question a bit better now. I don't know how far I travel during that braking time, and I don't know what that friction from the road is. And those are my two unknowns. I'll bet I can figure out both of those with the information that's given. Let's go ahead and do that. I'm going to grab myself a second dry erase board. And we'll relate that back later on. Let's see. I'm going to write some equations. We have Newton's second law is that the acceleration is equal to the sum of our forces over mass. And in particular, we can take this to just look at the horizontal component. The acceleration in the x direction is equal to the sum of the forces in the x direction divided by the mass of the car. So we can ignore these two vertical forces when looking at the horizontal direction. All right. Excellent. So this is Newton's second law, N2L. What else do we know? So this is why things are moving, but we also we have several equations for acceleration. Going back to the AP Physics 1 equation sheet, the definition of acceleration is that it's the change in velocity over time, which is v final minus v initial over our time interval. And looking at this equation, I can say, oh look, I know this, I know this, I know this. I can figure out what my acceleration is. Now, last but not least, this sum of the forces in the x direction. Let's add up all the forces in the x direction. That's going to be rightward forces minus leftward forces. Well, in our picture, there are 0 rightward forces, and there's just the 1 leftward force. So we're a negative force that the road exerts on the cart. And now we're good to go. I've thought through what equations I have. I've added up the forces. I've related that to the acceleration of the cart, and can compute the acceleration. Which one of these do I want to do first? Well, this is the one where I know everything, so let's go here. The acceleration must be equal to final minus initial, which was 25 meters per second minus 30 meters per second over my time interval, which I believe was 2.6 seconds. So my acceleration is negative 5 meters per second divided by 2.6 seconds, or plugging that into a calculator real quick, I find on 5 divided by 2.6 equals 25/13. That's not helpful, but 1.93 is. 1.93 meters per second squared. Cool. I now know the acceleration. That's one unknown that I have figured out. What else could I figure out? Well, now I know both mass and acceleration. So I can figure out the sum of the forces that must be acting on this car. So let's go ahead and apply Newton's second law next. I want to highlight this is a very non-linear process, right? We're just kind of seeing what we can do. I'm going to rewrite Newton's second law in the x direction now. And I'm going to, since this is the unknown, I'm going to rearrange this equation so it's the subject of our sentence. In other words, so that it's by itself on one side of the equal sign. And we do that by multiplying each side by m. And we are left with the sum of the forces in the x direction, that's this side of the equation, equals the mass times the acceleration in the x direction. We know that it's a 2,000 kilogram car. We just computed that acceleration to be 1.93 meters per second squared. So the sum of the forces in the x direction, this is a negative, I forgot to mention that. Negative, I forgot the negative sign there. right? It's because I ended up slower than I started. It's also good that it's a negative because my velocity change and therefore my acceleration is in the negative direction. Negative velocity change gives us a negative acceleration number, which I really need to plug in to Newton's second law. Anyway, 2,000 times 1.93, I'm going to grab my calculator, times 2,000 equals 5,013 is unhelpful, but 3.85 is helpful, and it's a negative 3.85 newtons. Remember that a newton is a kilogram times a meters per second squared. So multiplying these units together gives us a newton, which is our unit for force. All right, and then the last thing we can do with all of this, well, we can use it to figure out how much friction force there is. The force that the sum of the forces in the x direction we said was equal to negative the force that the road exerts on the car. And therefore, our negative 3.85 newtons of force equals the negative friction force that the road exerts on the car, or multiply each side by -1. That friction force is equal to +3, or its magnitude is 3.85 newtons. Is probably the best way to say that. All right, folks. I think that does it for us. That's all we could figure out. I guess the one more thing, which we learned about in the reading more than anything else, and this is something you may remember from forces in motion. I'm running out of clean, dry erase boards here, is we can figure out the gravitational force. The gravitational force exerted on an object, and we want to use the Ekina notation. The force that the Earth exerts on the car is equal to the mass of the car times the Earth's gravitational field strength. I will expect you to say all three of those words every time we're talking about little g, gravitational field strength. It's not just gravity. Anytime you say gravity is 9.8, that sounds to me like you're saying the electricity is 7, right? That doesn't make any sense. The gravitational field strength, it has a value on Earth of 9.8 newtons per kilogram. That's what I want you to say each time. Anyways, with that, the force that the Earth exerts on the car must be equal to 2,000 kilograms times 9.8 newtons per kilogram, which the force exerts on the car, therefore, is, grabbing my calculator again, I could probably do that in my head if I thought about it, but I don't want to think about it. So 2,000 times 9.8 is 1.96 times 10 to the 4 is how my calculator is outputting that, newtons, or, what is that, 19,600 newtons, if we don't want to use scientific notation. Let's look at units here. We had 2,000 kilograms times 9.8 newtons per kilogram. The kilograms here cancels with the 1 over kilograms there, and we're left with newtons overall, which is the unit for force. So that does make sense. All right, so we can figure out the force that the Earth exerts on the car, and then because that happens to be equal in this case to the upward perpendicular force here, this force must be that same 19,600 newtons. So that's a sample of things that we can figure out from this problem. Hopefully that was helpful, and if you have questions, please let me know.